Hey guys, and welcome to this video to help us kind of lay the foundations for a really cool exploration of how to write definite integrals as a limit of Riemann sums. So let's consider this function right here, y equals f of x, and let's try to find the definite integral from a to b of f of x dx, right, which we can think of as this area right here enclosed between the function and the x-axis. Now what we've done so far is we've calculated this by doing a sum of either little rectangles or perhaps trapezoids. And so let's explore this sum of rectangles idea a little bit more. Let's try to find the area under this curve from A to B. So the first thing we're going to do is we're going to divide this entire region into n subintervals of identical width. Now if they're of identical width, right, and we know that this whole distance right there, that whole distance is b minus a. That's the kind of full width of this interval. And if we have n identical subregions, then we know that each one of these subregions, and we're going to say that they have width called delta x, we're going to say that delta x right here is the entire width of that interval, b minus a, of course divided into n subintervals. So we're going to say that the width of each subinterval, delta x, is going to be equal to b minus a over n. And so we may use these two interchangeably, either now during the exploration or later on when we're doing some actual problems. So let's take a look at what the x values are going to be at each of our subintervals. And so let's call this first one right here a, and let's call this last one out here, let's call that b. Okay, so here are our different subintervals. Here we've got our first subinterval, and our second subinterval, and our third subinterval, etc., etc. So we know that the width of each of these is delta x is b minus a all over n. And so I think that if this right here is delta x, then I believe the x-coordinate right here at the end of our first subinterval is going to be, well, a plus delta x. So that's going to be a plus delta x. We have another delta x here, meaning that at the end of our second subinterval, this x-coordinate right here is going to be a plus 2 times delta x. Right? And then we'll have another delta x here in our third subinterval. And then this x value will be, well, a plus 2 delta x plus another delta x, a plus 3 delta x. Right? And we can continue this ad nauseum until we get to the point where we made it all the way to our last x value on the whole interval, which is b. What's interesting is that you can see that this is going to be a plus n times delta x, right? Because there are n of these subintervals. I'm going to go ahead and substitute this expression back in here for delta x. What's really interesting is you get, well, a plus n times, well, delta x is b minus a over n. These two n's will cancel out. So we get a plus b minus a. Of course, these two a's are going to cancel out now. Oh, and no surprise, we end up with the next coordinate of b, right? Exactly what we had expected before. Okay, not bad. Not bad at all. Great. So now we have the x values at each of our subintervals and the kind of endpoints of each of these subintervals. So let's designate k as our index, and that's going to be the variable that tells us which rectangle we are on, all these rectangles. So here's a picture of what we'll call the kth subinterval, right? Maybe it's the first, maybe it's the second, maybe it's the seventh, who knows, the kth subinterval. What are the x values of the endpoints of that kth subinterval? So for instance, let's look at the third subinterval here for a moment. I'm going to go ahead and zoom in on that. Fantastic. And so at the left endpoint, we had a plus 2 delta x, and at the right endpoint, we had a plus 3 delta x. And perhaps you feel comfortable generalizing that to say, well, if this is the kth subinterval, then, give me a moment. Well, the left endpoint of it is going to be, well, our lower limit of integration plus k minus 1 times delta x, right? If this was our third subinterval, this was a plus 2 times delta x. And our right endpoint will just be a plus k times delta x. Okay, so now we have the left and right endpoints of our kth subinterval. All right, let's make our way towards the next page. So for the purposes of this exploration, let's use rectangles, and let's sum up a whole bunch of rectangles in order to find the area under the curve, in order to find this definite integral. We do know that there's a trapezoidal sum, there's a midpoint sum as well. Let's just use a right-handed endpoint rectangle, and that's going to really aid us in kind of understanding this exploration here. And since we know for each of these subintervals we're going to have some sort of rectangle, we know that the width of each of these subintervals is going to be delta x, just as it was before. And now we want to think, what is going to be the height of the kth rectangle? Well, it's a y value, so we know. So it's going to be f of something. If we're going to be a little more mathy, we could say it's f of x sub k star, which this is an x value in the kth subinterval. So we're saying some x value in here, but that's a little vague. So let's go specific, and like I said, let's use a right-hand endpoint here. So given what we wrote above, the height of the right-hand rectangle would be, well, we know that this is going to be an x value of a plus k times delta x. So the height of the rectangle is going to be f of that, right? That height right here, the value the function takes there. So that would be f of a plus k times delta x. And I'm going to write this again with not a delta x, but with b minus a over n. So we have both of these notations here. Let's take a moment to think about that one more time. We spoke about the x value on the right-hand side of the kth subinterval, and we said that that x value was going to be a, right, as the left-handed limit of integration over here, plus k times all of those delta x's, and that's how we get to that right-handed endpoint. And we've decided to do a right-hand endpointed rectangular Riemann sum. So the height is going to be that right there, f of a plus k delta x. Delta x is the same as this right here. Fantastic. So the area of the kth rectangle, well, the area is the base times height. We know that the base was f of a plus k delta x, right? That was the width, that was the height, excuse me. And we know that the width was delta x, right? That is the width right here of that rectangle in that subinterval. Okay, so the sum of the rectangles, or the sum of the area of the rectangles, is going to be the sum starting from k equals 1 to n. So it's saying how many subintervals we're going to have, right? So from k equals 1 to n many subintervals of f of a plus k delta x, right? This is going to be, for each k, this is the height of that right-handed rectangle times delta x. That is the width of each of those k subintervals. And of course, that is going to be the area of the kth rectangle. Right, that expression right there. And then we're going to sum up the areas of all those rectangles. I'm also going to write this again, instead of with delta x's, I'm going to write it again with the b minus a over n. So that's k equals 1 to n of f of a plus k times b minus a over n times b minus a over n. Right, note to self, all we have here is that this expression right here, b minus a over n, and we discussed that is the delta x, that is the width of each subinterval. And so here's the question I think we asked in class last time was, okay, so we're summing up the areas of all these rectangles. How do we get those rectangles to be a better and better approximation for the actual area underneath this curve? As you can see, right, this rectangle right here is going to be an overestimation. Well, let's take a look at this graph right here, and here is one way to visualize these rectangular approximations of the area under this curve, and they're all of uniform width. Of course, we know that the more of these rectangles there are, the better our approximation will be. If we increase the number, the more and more and more, they each become thinner, and you can see that these overestimations or underestimations become less significant, and the sum of the areas of these rectangles becomes closer and closer to the actual area under the curve, the definite integral. And of course, as the number of rectangles increases towards infinity, that's when this Riemann sum approximation of the areas of these rectangles will become infinitely close to the actual area under the curve, the definite integral. And so, what we can say is, aha, how can we get those rectangles to be a better and better approximation? Let's take infinitely many of them. So we'd say here the limit as n goes to infinity of the sum, k equals 1 to n. So we're saying, right, we're going to now, the limit as we go towards infinitely many of these subintervals of, well, exactly what we were summing up here before, right? I can use this expression right here, or I can use this expression right here, one and the same. I'll use this one out here, right? That is going to be f of a plus k times b minus a over n times b minus a over n out here, right? Note to self, right? This right here was the height of the, what I'll say, the kth rectangle, and this was the width of the kth rectangle. And we're summing up the limit as k goes to infinity as our limit of the number of rectangles goes towards infinity, right? And this right here is going to be the right-handed x value of each of those rectangles, because we're taking f of that x value, so this is going to be the height of it, and this will be the width of each of those uniformly sized rectangles. And as we sum this all up, that will be the area under the curve, that will be our definite integral. So that was a nice little intro to what's coming up soon. Looking forward to seeing you and picking up where we left off.